Now I've got another circuit. The purpose of this one is to basically divide the frequency of a clock line to slow it down. So we'll call this output Q0. So what we want is on each positive clock edge, Q0 changes state. And effectively what that does is it halves the frequency of the clock, right? Because the clock line has two edges, positive and a negative edge. And if Q0 changes state only on every positive edge of the clock, that means whatever the frequency of the clock line is, the frequency Q0 will be half of that. So I've got a circuit there that does that. It's basically just a flip-flop where the output back feeds via a NOT gate into the input. So in every positive edge of the clock line, Q0 will change state. And so we can play with that and see that effect. So in every positive edge, Q0 changes. And we can also demonstrate that the frequency is halved by looking at a timing diagram. We have to mark our clock line as well. There we go. So in every positive edge, Q0 changes state. So we can see that the output frequency Q0 is half the input frequency of the clock. I suppose we wanted to divide this further. Naively, what we could do is we could daisy chain these circuits together, right? So I could get another copy of this and have the clock into the next flip-flop be the output from the previous one. So we can label this Q1, and then we can go, in fact, it's probably better to stack this vertically. I think it'll be a little cleaner. So we'll clean this up a little. So the output from the previous acts as the clock input for the next, and we'll have one more layer for Q2. So the output here routes into the clock line of the next. So again, let's have a look at our timing diagram. And on the face of it, it seems to do the right thing, right? So Q0 is toggling on every positive clock edge. Q1 is toggling on every second positive clock edge. Q2 is toggling on every second, then every fourth, then every eighth, and it's like every stage is another divide by 2. And on this level of timing, everything seems to be fine. The problem is when we go down to the single step, when we include the propagation delay for the flip-flops, this actually has some undesired properties. So if we simulate this in single step mode, what we would like is that all the outputs update to what they should be simultaneously. This is not the case. When the clock line goes high, single step mode. So we're running it in single step mode. When the clock line goes high, we have to wait for the effect of the first flip-flop, which will turn on Q0, and that then flows into the next flip-flop, which turns on Q1. That then flows into the next flip-flop, which turns on Q2. So they don't all happen simultaneously. The timing diagram only shows the behavior up to the next clock edge. So if we replace this with just a generic input, and we pretend it's the clock, then what we can do is we can observe the behavior of the timing diagram at a much higher resolution. So we turn on the clock, and we can see all the outputs only change. So to replicate that behavior, we have to click on Show Single Gate Steps in the data graph. So that way it'll update only, it'll show us every propagation layer along the way. So we turn on single step mode, and the clock line goes high. First Q0 goes high, and then just slightly afterwards Q1 goes high, and then slightly after that Q2 goes high. So you can see there's a sort of a ripple, right? It flows through. And then if the clock line goes low and high again with this ripple effect, they're not all updating at exactly the same time, which is undesirable. So how do we do this? The problem is that this is not a synchronous circuit because not all the components share the same clock line, right? The clock input for the second flip-flop is not the global clock, but the output from the second flip-flop. So what's a better way to do this? So one solution to the rippling problem to ensure that the circuit is sequential is instead of using D flip-flops, we can use D flip-flops with an enable input, which digital represents as registers. Each flip-flop is wired as it was before, so the output is the negation of the input, with the exception now that the first flip-flop is always enabled, so nothing's changed there. For the second flip-flop, it's only enabled, it'll only update if the previous one is on, and for the last flip-flop, it'll only update if the previous two are turned on. So if we run this in single step mode, when the clock line goes high, this will engage the clock of all the registers at the same time, and so all update sequentially. Toggle the clock line again. And so this means we no longer have any skew. They all update at sync, or at least up to the rate at which the flip-flops update. So if each flip-flop has a propagation delay of, say, 50 nanoseconds, it doesn't matter how many of these you put in parallel, because the combined propagation delay will still be 50 nanoseconds because we update all these in parallel. Not like before, where the gate, the clock line of the next flip-flop was hooked to the output from the previous one. This means you get this like ripple delay, which means one, obviously it takes a lot longer to update everything, and two, it means you can transition in through states in between that you wouldn't want to, because that might affect the behavior of something else. So this is, in a sense, a much better design because it avoids that problem from before.